Hello everyone, this is Pooky Code and welcome back to Neural Networks Explained Part 9 where we will look at gradient descent and why it works. So let's get started. Okay, so now I want to introduce a concept that is called gradient because you've heard me talking about gradient descent all along, but we don't even know what a gradient is. So a gradient is a vector, or a list of numbers if you prefer, is a vector of the partial derivatives of a function. So what this means is that, for example, if I have this multivariable function, f of x, y, z is equal to 3x plus 4y minus 5z, I would take the partial derivative for each variable, so del f over del x, which would be del of 3x plus 4y minus 5z over del x, and I would see that since I am deriving with respect to the variable x, then 4y minus 5z is just a constant, and then 3x is like the linear form, and 3 is the slope. So we get as answer, what is the slope? With respect to x, it's 3. Del f over del y, you apply the same logic, so 3x minus 5z are constants, we don't care about it. We have 4y, and thus the slope is of 4, with respect to y, of course. And then we have del f over del z, which is del again, and then you differentiate with respect to z here. And you'll see that it gives us minus 5. So the gradient of a function f is written as follows. So it's kind of like a Doritos chip with a f, and it's called nabla symbol. It's a nabla symbol, but you can pronounce it del. Personally, I just like to call it the gradient of f, and it can be represented as a vector. So the vector of each partial derivative, so each variable, so del f over del x, del f over del y, and del f over del z. And in our case, since we calculated each of them individually, we put them back where they belong, and we have the vector 3, 4, minus 5. So now our goal is to reduce the cost function by taking steps that reduces the value of the cost function. So we imagine that we start our neural network with random weights and random biases, and at first it's going to produce garbage, but then our goal is to adjust the weights and the biases by going in a certain direction such that it minimizes the cost. So we're now going to talk about directional derivatives, and you'll see why it is useful. So a directional derivative is the slope of f after taking a step in a certain direction of a certain length. So for example, given a vector v, the directional derivative measures the slope of f when moving in direction v, or more precisely, the instantaneous slope when moving in direction of the vector v. And when calculating directional derivatives, we will make sure that every direction of every vector v will have a magnitude of 1, and that is very important for us. So we want that when you have vx squared plus vy squared, square root of that, we want that to be equal to 1. So that's the magnitude. So for example, the vector 1, 0 works, the vector 0, 1 also works, the vector 1 over square root of 2, 1 over square root of 2 also works, since they all give a magnitude of 1. And so we will denote directional derivatives of a vector v for a multivariable function f as the nabla symbol, so del, and then v and f of x. Personally, I would just say the directional derivative of f with the vector v. So I'm just going to go back to single variable calculus, and then you'll see a very important fact that we need to notice. So we remember that we had functions in single variable calculus that for a function f of x, then df over dx is a function that gives the instantaneous slope at a certain point. So we can approximate the change in f so the change in f is delta f. It's approximately equal to df over dx times the change in x. And why is that true? This is because as delta x gets smaller and smaller, it is approaching the instantaneous slope. So you can think of it as the delta x kind of becoming closer and closer to the dx. So this kind of becomes like df is equal to df over dx times dx, and they both cancel out. So this is intuitively how it makes sense. So if I repeat, it means that if you take the instantaneous slope at that point, you multiply by the change of x, this gives approximately the change in f. And it becomes more precise when delta x, so the change in x, is smaller. So we then recall that the directional derivative is the total change in f over the total change in v as v gets scaled down, so as it becomes an instantaneous directional derivative. So we're also going to do the same thing we did with single variables, and we're going to approximate the change in f. So we have that the change in f is approximately equal to del f over del x times delta x plus del f over del y times delta y. And I want you to notice a very important fact. This expression looks awfully similar to this. It's kind of like a copy pasta of it. But instead of putting df over dx, we have del f over del x since it's a multivariable function. So how do we interpret this? It makes sense because it means that the total change in f is equal to the total change in f due to x and the total change in f due to y. So as you can see, this represents the total change in f due to x, and this represents the total change in f due to y. So you can kind of imagine as if f was just a single variable function and it only had as parameter x, then the change in f due to that x would be the formula we had up there. So df over dx times delta x. But we substitute with the appropriate terms and we have del f over del x times delta x, and you have the total change in y, total change in f due to y, it's equal to del f over del y times delta y. Alright, okay, so we finally have that the change in f is equal to del f over del x multiplied with delta x plus del f over del y times delta y, and you can represent that more compactly with the dot product. So we have that the change in f is equal to a vector that strangely contains all the partial derivatives of each variable multiplied, dotted with a vector that contains the change in x and the change in y. And so our goal is to make sure that delta f is the lowest possible. So we want to minimize the change in f. And I'm not talking about minimizing as by minimizing the scale of it, but by minimizing it. So if it can be negative, then I want it to be negative. So if the change in f is equal to minus 20, that's much better than having a change in f of plus 3 in our case, because we just want the cost to go down, 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 and down. So an important fact about the dot product is that it has another interpretation. So other than multiplying each element one by one, so one element with its next element, one element with the other element, this element with the other element, when you have a vector v and a vector w, then the vector v dotted with the vector w is also equal to the magnitude of v multiplied with the magnitude of w multiplied by the cosine of their angle between. So I'm just going to prove this, If you don't want to listen to it, that's fine. I will speak about the intuition later, so you can just skip to that part. So we know that the vector v is equal to, if you refer it by the magnitude of v and only by its angle, so we have v and then alpha, meaning the angle from the x-axis, and we have w here with its angle from the x-axis, which is a beta. Then we know that v is equal to the magnitude of v times cosine of alpha and the magnitude of v times sine of alpha. And why is that? Because if we have a right triangle, and this is the magnitude of v, and we have an angle alpha, then this vertical component is equal to v sine alpha, so magnitude of v times sine alpha, and this horizontal component is equal to the magnitude of v times cosine of alpha. So you can verify it with your SOHCAHTOA if you still remember it. So opposite over hypotenuse and all that stuff. We also have that the vector w is equal to the vector, a vector of the magnitude w multiplied with the cosine of beta, and the other entry is the magnitude of w multiplied with the sine of beta. So if you want to look at what the hell this means, I really suggest you looking at Khan Academy's video on trigonometry, because I've learned a lot of it from there, and that if you're aware of it, then if you still haven't learned it, you will learn it at school. So I'm just now going to expand our dot product. So we know that the dot product is multiplying each entry with the matching entry from the other vector. So we have that v dotted with w is equal to this part times this plus this part times this. And as you can see, this is written down below. So magnitude of v, magnitude of w, cosine alpha, cosine beta, plus magnitude of v, magnitude of w, sine alpha, sine beta. You can put magnitude of v, magnitude of w outside, and then you'll have magnitude of v, magnitude of w, multiplied with cosine alpha, cosine beta, plus sine alpha, sine beta. And if you know what the cosine angle addition identity, this just reduces to cosine of alpha minus beta. So you really should watch Khan Academy's video on the cosine angle addition identity if you don't know what that is. Or you can just listen to the intuition later. So you do you, alright? And alpha minus beta, and since cosine is an even function, then I can just flip the sign, so put a minus times alpha minus beta, which gives me beta minus alpha. And we know that beta minus alpha is theta, so the angle between the two vectors. And so we have just concluded our proof. So QED, so little rectangle. So now back to our directional derivatives. We have that the change in f is approximately equal to the vector del f over del x, del f over del y, dotted with the change in x and the change in y. And then we're going to substitute it with the interpretation of the dot product we just found, and we'll see that the change in f is approximately equal to the magnitude of that vector of the partial derivatives multiplied with the magnitude of the delta x, delta y times cosine of theta, where theta is the angle between these two vectors. So we know that del f over del x, del f over del y, we don't have any control over, and delta x and delta y, we are going to fix the magnitude to be of like 1, for example. Then our goal is to find, okay, I have a vector that is a gradient, it's fixed, I have a step to take, and it has a fixed length. Then which direction should I choose so that delta f is the smallest possible? So the only thing that we can vary is cosine of theta. So for example, if I have the gradient is this one, this is the gradient, without Apple Pencil. I write so bad with my fingers. Without the Apple Pen, no. So you have the gradient, and then for example, I would have this, which would be the vector delta x, delta y, and I would say it's a dot product greater, smaller than, for example, having it here, or having it here, or here, or here, and all this. So we want to find the optimal direction to take to reduce the value of f. And then we can only change cosine of theta, right? And we know that by definition of the function, we know that cosine of theta is bounded from -1 to 1, and so the smallest value cosine of theta can take is -1. And when does that happen? This happens at cosine of pi radians, or at cosine of 180 degrees. So we can now conclude that to minimize delta f the fastest, we calculate the gradient and we move in its opposite direction. So basically we want that the step we're taking and the gradient are separated by an angle of 180 degrees. So that means if the gradient is here, you want to go here. And as you can see, if you have the gradient, del f over del x, del f over del y at the point xy, then you want to go the other way. So minus del f over del x, minus del f over del y, and this is the direction of steepest descent. So for a function f of x, y, if you are at the coordinate x, y, then you should go to optimize and to minimize f, you should go to x minus del f over del x and y minus del f over del y. So in the opposite direction of the gradient. So the cost function is a function like any other function. So that means we can use gradient descent and we can minimize the value of the cost, which is exactly what we want. So we can assume that if we have a fixed pair of input and output, so for example, I give 1, 0 and I expect to have a 1, so like the XOR problem, and I have a pair 1, 1 and I expect to get a 0, then this counts as pair. So I'm just going to take the pair 1, 1 gives 0, for example. Then we have that the cost function can only vary all the weights and all the biases, because you cannot change the value of what they're going to be at layer 2 or layer 3. You modify the weights and the biases to do that. So this means that the cost function for a given pair of input and output depends only on the weights and the biases. So we can have that C is a function that takes W1, 1 of the layer 1, W1, 2 of the layer 1, W1, 3 of the layer 1, W2, 1 of the layer 1, W2, 2 of the layer 1. So basically all the weights, and then B1, 2, B2, 2, and then basically all the biases. So we want to minimize C, so we have to calculate the gradient. And we have that the gradient of C is equal to del C over del W1, 1, 1, del C over del W1, 2, 1, del C over every weights and every biases. Alright, so before we were at this coordinate, so if you think of the neural network as being a point in a, I don't know how many dimensional Cartesian plan, then you would see that they would be at the coordinate W111, W121, W131, W211, W221, and all that. And then we know that to minimize C, because this is just like any other regular function, we can just go to the coordinate minus the gradient. So W111 minus that gradient, minus that partial derivative. So del C over W111, then W121 minus del C over W121, then W131 minus del C over W131, then W211 minus del C over W211. So it gets kind of repetitive, but basically you understand that we have to update each weight and each biases by subtracting the gradient. So the matching element of that in the gradient. So if you have W111, you want to subtract del C over W111. So the partial derivative of C with respect to W111. And in practice, we won't just subtract the gradient because that would just make a huge step, but we would subtract the gradient scaled down with like 0.3 or like 0.03 so you can take smoother steps. And this value, 0.03, 0.3, is called a learning rate. So we now know that the learning algorithm for learning neural networks consists of pretty simple steps, yet so hard to understand. So you first have to initialize weights and biases at random values centered around 0. Then you feed inputs. You calculate the value of the cost function. You calculate the gradient of the cost function. And then you perform gradient descent. And how do you do that? You subtract the gradient from the weights and biases. And you have to make sure that when you're subtracting, you make sure you subtract the value correctly. So when it's W11, you want to subtract the entry del C over del W111. And of course, in practice, we would scale the del C over del W11 with a learning rate. So make it maybe 0.3, 0.01, I don't know. And so this was it for gradient descent. But we still haven't looked at backpropagation. But fear not with me, we will succeed, okay? We will succeed. We will learn about backpropagation. And so, I hope you like this lecture for today. So thanks for watching. If you like this content, like, subscribe, do all that good stuff. And in the next video, we are going to look at the backpropagation algorithm, or more precisely, how to calculate the partial derivative of each weight and biases. So stay tuned.